Hey guys, in this video we are going to discuss Newton's divided difference. So we know that in my previous video we have discussed Lagrange interpolation polynomials. So if you are given a data set, say we here how many data points do we have? We have n plus 1 number of data points. So we can compute cardinal functions very easily because we have an expression for that. The thing is, the the disadvantage of using Lagrange interpolation is, so suppose you want to add another experimental data point, so you want to include another data point into your calculation. Then what you had to do, so if you are following Lagrange interpolation method, polynomial method, so you have to recompute these cardinal functions. So that is the disadvantage of Lagrange polynomial. So in order to avoid that negative point, today we are discuss Newton's divided difference. So here, so this is your data set. So if you once you have the Newton's difference interpolation polynomial, so you can include data points after that. So that's the plus point, that's the advantage of Newton's method. But here Lagrange interpolation, if you want to add another point here, you have to recompute these cardinal functions, right? That's the thing, that's the bad thing about Lagrange interpolation method, right? So this is the thing, right? So we compute polynomials recursive, right? So here we will describe an algorithm in a recursive form. Suppose we have this polynomial, kth order polynomial, that interpolates k plus 1 data points, right? So now our goal, so if we have this kth order k degree polynomial, now then we compute k plus 1 degree polynomial by using this polynomial we have, right? So we interpolate, this is the k plus 1 degree polynomial that interpolates one extra point. So if you add an extra point here, x n plus 1, here x k plus 1 and y so k plus 1. If you add this extra point, so we interpolate this polynomial by using the previous polynomial we had. So that's the main idea of Newton's divided difference method, right? So let's so now we are going to prove that one. So let's get an idea, let's try to understand what this is, right? So here we start off with this one here, when so n equals 0, right? Initially we have this data point, and this is our, so suppose we have this one, we start off with this data point, right? x0 comma y0, right? So what is the polynomial that goes through? So what is the polynomial? So this is your x0, right? And this is the corresponding y0, right? So basically this point. And what is the polynomial that passes through this point, which is a constant? You can consider constant. So p sub 0, which is the polynomial in x. So what is the degree of this polynomial? Because here we have a 1, we have a data point, so degree of this one is 0, that means constant polynomial. So the output should be y0. So initially if we have, yep, this is the polynomial that passes through this point, right? Now suppose we have two data points. When n equals 1, that means we have two data points. Say this is x0 and the corresponding y0, and this is your x1, the corresponding y1 is this. So now we are going to find, so when n equals 1, that means we have two data points, x1 comma y1, right? x0 comma y0, x1 comma y1. So basically we have two data points. Now so basically what we did, we add this point to this one here. Now using this one, we compute the interpolation polynomial that passes through these two points, right? That's the idea. So using this previous polynomial, using this p0, so we find a polynomial which passes through these 2 points. So that polynomial is denoted by p sub 1. So we know that this polynomial evaluated at x0 should be equal to y0. So when you sub x0 into this one here, we should get y0. So then what I do, I put, so this is my p1x. How do I define this? I define this polynomial using my previous polynomial. Let's put this like this, or put in this way, p sub 0 of x. When you plug this one into here, we should get y0, right? And when you plug this one into here, we should get y1 from here, right? So we had to do like that, right? When you throw this number into the polynomial, so we know that this is a constant polynomial. So when you throw this number into polynomial, we get the same value. This p1 returns the value of y0, that is okay. But if you throw this number into here, we should get y sub 1. So what should I do? This polynomial always gives us the value of y0, right? This gives us the value of y0 all the time, this one here. If you add a term like if you cancel this one with yep, if you add a term like this, right? So what happens when you throw this number into the polynomial? This term kills, right? So when you throw this number into here, right, what happened to this term? This one vanishes, this term vanishes, right? We only get this one, p sub 0 of x sub 0. So we know that p sub 0 anyway returns the constant value y 0, right? Alright, this cancels when you plug this number into the p1, right? This cancels. Anyway, we get a y sub 0 from here, right? So when you plug the other one here, other value y1 into here, so anyway we get y0 because it is constant here. This is a constant polynomial. Anyway, we get y0 from here when you throw this number into the polynomial, and from here when you throw this number into the equation, we should get yep. So this is the equation here. We want to get y sub 1, right? We want to get this y sub 1. When you throw this value into the polynomial p1, we want to get y sub 1, and this will return y sub 0 here. This is the constant one, and we can find this constant, right? And this is converted to x sub 1, right, minus x sub 0 when you throw this number into here. I think this one is clear now. Now you solve this for a sub 1. Now you solve this for this constant. So I erase these things, then you can clearly see what I said. Alright, okay, then you solve this equation for a sub 1. This is the corresponding coefficient you have to add. When you add this coefficient, that means when you throw this one into the this polynomial, this returns the value of y sub 1. How? Let's check that one. Alright, let's check. Basically we have p sub 1 of x is equal to here this one y sub 0. It's a constant value for all x. This returns y sub 0, the value of y sub 0, and we found that a sub 1 is this garbage, y sub 1 minus y sub 0. Here we are checking whether this returns this value when you substitute this one into the polynomial, right? So here you have x1 minus 0 times minus x0 times. So when you throw this one into here, this becomes x1 minus x0. This is, we can cross this off. We end up when you throw this number into here, so p sub 1 evaluated at x1 would be y sub 0 plus what are the remaining things, y sub 1 minus y0. Can close this off. Aha. So p sub 1 evaluated at x1 gives us the same value here. All right. For this, so that's the thing. So this is the corresponding coefficient you have to add when you add this one. So you get when you throw this number into the polynomial, you get that corresponding y value. So that is the checking part. Now suppose you want to add another point, say x sub 1, x sub 2, and the corresponding y value is uh, y sub 2, and this point, right? You want to include this one, right? Now you want to find the interpolation polynomial which passes through these three points using this previous polynomial. All right, let's look at that case when n equals 2. That means basically we have three data points, x0 y0 comma x1 y1 comma x2 y2. So basically we have three data points. So we are finding the polynomial interpolation which passes through these 3 points using the previous polynomial. So what do? You add this term. So this is your previous polynomial p sub 1, and this is we want to find this one. So how do you define that a polynomial? This is our polynomial. This polynomial passes through these 3 points. P1 would be the polynomial which is passing through these 2 points, right? And we add this term, right, as before. Earlier we added a constant time x minus x0, right? So now we add a constant time x minus x0, x minus x sub 1, right? This one. So let's now what we do, we solve. So we know that this polynomial evaluated at x0 should be equal to y0, right? And we know that x sub 1 evaluated at this point also equal to y sub 0 here. So here x0 evaluated at x0 is equal to y0, and x evaluated at the polynomial p1 evaluated at x sub 0 is equal to y sub 0, and this is clear, right? So when you plug this, when you throw this value into the equation, this cancels off, right? This term kills, right? You can kill this term by throwing this value into the equation. So what do you get? We get p sub 2 evaluated at x0 is equal to p sub 1 evaluated at x0, which is y0 from here. Right, this is clear. Now check whether this polynomial evaluated at this one returns the value of y sub 1. Let's check. When you throw that value, when you throw this x sub 1 into here, so what is the value of p sub 1 of evaluated at x sub 1, which is y sub 1, right? Y sub 1 here. y sub 1, and this becomes y sub 1. When you throw this value x sub 1 into this polynomial, we don't get this term, right? So this becomes 0. So this is p sub 1 evaluated at x sub 1, which is equal to y sub 1. Then p2 evaluated at x sub 1 would be y sub 1. This is clear, right? Then from the next data point, when you throw this one into here, we should get y sub 2 here, right? So from this data, you find this value, this constant value, because if you throw this number, this x sub 1 into the equation, we should get y sub 2. From that data, we find a sub 2, which is this one also clear. So when you do that one, finally you can find that constant would be y2 sub 2 minus p polynomial p1 evaluated at x2 divided by x2 minus x0 times x2 minus x1. So you can do this calculation, right? You can see that here you get this constant a2, right? You can check this work, right? I think you can understand that why did we add this additional term. So when you throw x0 and x1 into here, when you throw x1, first consider x1, when you throw x1 into here, you don't get any, so this will not contribute anything, right? So we know that p1 evaluated at x0 is equal to y0. That's because we want to we want this polynomial to pass through that data point x0, right? Data point x0, this is x0, yep, this is x0 and y0, right? Yep, x0, y0, x1, y1, and we have another one x2, y2, right? So we want this polynomial pass through these all points. When you throw x0 into here, this won't gives nothing, right? So only we get when you throw x0 into here, we get p sub 1 evaluated at x0, which is equal to y0. Then so this polynomial passes through x0 comma y0. Let's check this one as well. If you throw this number, this x1 number into the equation, so this becomes 0, right? Does not contribute any value when you throw this value into here. So but if you throw this one into here, p sub 1 evaluated at this point would be y sub 1. That means p2 also passes through this point. So next one, so we want this polynomial to go through this point as well. That's why when you throw this number, we want the function value, the polynomial value at that point a is equal to y2. Therefore we can find this constant of a2 like this, right? This is clear, this is much clear. So here I would like to expand this coefficient a sub 1 right? So this is our, so to recap what p sub 1 is, this is our p sub 1. When you throw x sub 1 into here, you get something like this. Right. So what I do here, I add x1, and I subtract from the same, I subtract this one from the same value x1. So here I did nothing, right, because this cancels with this, right? Now I expand this one, I distribute this factor, I expand this brackets, right? When you expand this bracket, right, I consider this one as a 1 unit. So this one, so here you have y naught, y sub naught plus this one times this factor x2 minus x1 plus this factor times other one x1 minus x0. This step is clear, right? So you can close this off, and simplify this. Here you have y sub 0 that cancels with this y sub 0. I mark that one in a different color. Yep. Then I end up with having y sub 1 plus this one, this term here, right? This is p, the polynomial p1 evaluated at x2, right? So you know that this value would be, what is the value of polynomial 1 p1 evaluated at this point? We know that that point is y2, this point would be y2. So take this term to other side, you can rearrange this equation, right? Sorry, wait a second, I don't do that. So what I do here, I throw this value. So this is our p sub 1, the polynomial 1 evaluated at x2. So I found this value in terms of y's and xi's. I throw this value into here, then I do simple manipulation. I throw that value into here. So with the small algebraic manipulation you get, so wait a second, I will zoom this. Yep, a sub 1, yep, a sub 1 is equal to this. So y2 minus y1 divided by x2 minus x1 minus y1 minus y0 divided by x1 minus x0, or everything divided by x2 minus x0. So what this mean? Let's find what the mean of this, right? So I'm going to a sub 1 coefficient. Here look at this. So y, the distance between y coordinates divided by x coordinate, distance between x coordinates. This is something like the gradient between these 2 points, right? So this is your x0, y0 coordinate, and this is your x1, y1 coordinate. So here this coefficient, right, is the slope of this line segment. If you join these 2 points with a line, straight line, so basically this a sub 1 means the gradient of this line segment, right? This line segment, right? The gradient, oh, this is not a straight line, if you join these 2 points with a straight line, perfect straight line, so this gives you, a sub 1 gives you the slope of this straight line. If you look at a sub 2, so look at that. So here basically we have 3 points, x0, x0 comma y0, other one is x1 comma y1, and the last point is x2 comma y2, right? Here look at this, the distance between y2 and y1, y2. This means the slope of this line segment, right, minus the slope of this line segment divided by x2 minus x. No, that's the thing. This is something like, so this is something like so this is approximate tangent or slope at this point. Yep, so this one would be the slope, the approximate slope at this point, minus the approximate slope at this point, something like that, right? This is something like approximate slope at this point, let's say like that, at x2 minus f prime approximate slope at x0 divided by x2 minus x0. What is this? This is something like approximately equal to the derivative of f prime evaluated at, let's say, x2. Look, this is something like f double prime evaluated at x2 or x0, something like that, right? So this coefficient a2 is approximately equal to double derivative of f evaluated at x2. Let's look at a1. That's the idea. This one is approximately equal to f prime of f prime evaluated at x1, something like that. If you have 1 here, so here you have prime 1, only 1 prime. If you have, you can argue like that, if you have 2, index is 2, if the index is 2, here you have double prime, something like that, right? So now we look at the general term. So now we go to discuss the general term. This is the general case. So assume that p sub n minus 1 polynomial interpolates these points these n up to n minus 1 points. That means this polynomial, let's draw a small graph. So this is your x0, x1 and x2 up to xn minus 1 n minus 1. So this polynomial p sub n minus 1 passes through these points. So this polynomial interpolates these points, right? So let's assume So now you add a point. So this is the new point x and yn. So I draw that point in a different color. Yep. So this is my new point xn comma yn, right? This is when you add. So now add this new point. So what do I do? I add this term, because when you throw these values into here, what happens? This will become 0 when you put these points. This term becomes 0, right? So now I consider this additional point. Now I add this additional experimental data into this data set. How many points do we have? N points. So with this one we have n plus 1 altogether, right? So now I add this additional point. So when I add this additional point, how do I interpolate these all points using the previous polynomial? This is the way, right? So what I do here, I add this additional one and find this coefficient using this point that I added to the data set to my that I added to my previous data set, right? So now I sub this value into here, and you can add that one, right? So you can find that coefficient, right? A sub n. Therefore, the Newton's form for the interpolation. So initially we had x naught, y naught, and then x1, y1. We recursively generate a polynomial for these one. Now I add x2, y2, this. I keep adding these new points, then I can generate. So from here I can generate p0, yep, p0, so which is y0, right? So from these two I can generate p1, right? So look at this is my p0 and this one is my p1. So p1, polynomial p1, right? If I add another point into my data set, then I can interpolate these 3 points like this. This is my p2 by using the previous polynomial, right? So this is my p2. I keep doing this, or you can add many points. So you can add another point, 3, y3, then you get p3. Or if you have, we keep doing recursively, right? Suppose we have until we, so this is the last point, xn, yep, xn, yn. So when you add this one, then finally we get this term. So I hope you understood this method. So once you add a new point to the your previous data set, you can compute the polynomial which interpolates those data points by using the previous polynomial, right? So I hope you understood this method. right? Let's My next video I'm going to discuss an example on this, right? So I hope you understood Newton's divided difference method clearly. So in my next video I'm going to discuss an example.